Alright, so in this video we'll look at something called an energy profile diagram, also known as a reaction coordinate diagram. And these illustrate the progress of a chemical reaction and therefore can illustrate in terms of energy how fast a reaction or the speed of a chemical reaction. So first of all, it's a graph, and the graph has potential energy or energy graphed on the vertical axis, and then it has the progress of the reaction graphed on the horizontal axis. It illustrates the path that a reaction takes, and it shows the amount of energy it takes to activate the chemical reaction. This has a fancy name. It's called the energy of activation, E sub A, energy of activation. And it shows the enthalpy, or the heat or the energy that's either released or taken in during a chemical reaction. So it'll show you whether it's endo or exothermic. So I have a diagram drawn here. I obviously have one from the book right here, but I have a little bit different one that I want you to draw. And we'll just start by drawing the basics of the diagram right here. And we'll start with the vertical axis right here. You should put energy on the vertical axis. And then on the horizontal axis right here, you should put reaction progress. Usually it's coordinated with time, or how long the reaction is going on for. And then it looks like a hill like this. And so the reactants, A plus B, start right here. Those are made-up reactants, A plus B. And then it drops down on this side and then eventually ends up at the products right here of AB. So A plus B goes to the products AB. Sometimes you won't see the reactants and the products written in there. Sometimes you will. And as you see in the book, they even have like the Lewis dot structure of the reactants and the product right here. Now I also have some arrows drawn in here, and those are really important because those are measurements that tell you about the speed or the progress of the reaction. If you draw a line right from the beginning right here, and it should be perfectly horizontal, I probably didn't do the perfect horizontal line right here, but this distance from the starting point right here, horizontal to that, to the very tippy top of the highest energy hill right here is called the activation energy, the E sub A, also known as the activation energy. And of course, the less activation energy something takes, the faster the reaction is going to be, the more speed it's going to have. And so the lower the little activation energy hill here, the faster the reaction is going to take place. Right at the tippy top right here, this is where the reactants come together and they form what's called an activated complex, also known as the transition state. This activated complex or transition state might be where the A and the B, or the two atoms or molecules or ions or whatever they are, orientate themselves in the correct phase, bounce together in the right way, bump against another atom, or have something help it so then it can react. And so it might be an intermediate that forms right here that's not A plus B, and it's not AB. It's something else, and it might only exist for a microsecond, but during this transition state, many times you see intermediate complexes form. They call them activated complex sometimes too. Then the complex finishes, and we are on a downward slope right here, and we end with the product AB. This distance from the very start to the very end, notice from the very start here to the very end here, this distance, this is our energy, our enthalpy of reaction. And so in this reaction, you can see that it starts higher and ends lower, and therefore it would be an exothermic reaction because some energy was given off. Now, if the diagram went here and ended like up here, for example, then our enthalpy change would be up here, and it would be a positive value, and you'd say that'd be an endothermic process. So a couple things to watch for when I show you lots of examples of these. First of all, watch to see if the reaction is endo or exothermic. So watch to see where it ends versus where it starts. Second of all, watch for an intermediate, or watch for this activated complex that forms right here and how that could be a little bit different from the reactants themselves. Third of all, watch for the activation energy, because that's the rate determiner. And the shorter the little energy hill right here, the faster the reaction is going to go. And then one strange thing that happens sometimes is that reactions don't happen in a single little activation energy hill. Sometimes there'll be more than one bump. Sometimes there'll be a starting activation energy, then there'll be another one. Sometimes there'll even be another one after that. And the one that determines the rate is always the highest hill, because that's the one that takes the most energy. So watch for those things throughout these examples that I'm going to go through. I'm just going to switch screens here for a second, and I'm going to open this up and present some examples to you of some various different activation energy diagrams. So here's one that has potential energy on the vertical axis, reaction progress on the horizontal axis, reactants right here, and notice how they kind of draw the Lewis dot diagrams. Then they have a transition state up here, and notice how this one is like OCONO. It's something completely different to what we had for reactants, and it's not anything like the products. So this would be called an intermediate that forms right here. Notice it had a positive activation energy, and then the complex split apart and became the products right down here of CO2 and NO. And you can see that that energy was exothermic because we started higher than we were before. Here's a second example, and this one you'll notice starts lower and ends higher. And so this one right here would be a good example of an endothermic reaction. You can see this also shows this reaction forming right here, and there's an activated complex right here that's kind of an intermediate that's not the same as the reactant or the product. So that's another example. Here's an old multiple choice question. This says, the energy profiles of 4 different reactions are shown below. The scales are the same for each. Which reaction is the most exothermic? Okay, so a lot of kids get tricked here, and they start to look at this activation energy right here, and they pick this one right here because it's got like the tallest hill. But remember, this measurement from the start to the tallest hill is the activation energy, not the enthalpy, which would tell us if it's exothermic or endothermic. And so what you want to look at is from the beginning to the end, and notice how big a distance there is between this beginning and this end. From here, you're actually going up, so that would be endothermic, so that would be the wrong answer for sure. This one goes down some too, not quite as much as this first one right here. And then this last one, you'll see it goes up once again, and so that would be endothermic again. So it can't be B, it can't be D. Only A and C are exothermic, and you can see this one drops the most from reactants to products. So A would be our most exothermic reaction. All right, take a look at this one. I said we'd find some that sometimes have more than one intermediate or more than one activated complex or transition state. And you can see we start here with this reactants, and then this is an activation energy, and we form something that's not anything like the reactant and not anything like the products. And then it goes down a little ways, and then it has another transition state right here. So this would be called a multi-step or a two-step process, and it has a second activation energy right here, and then that splits and comes down here and becomes these products right here. So this is a multi-step reaction. You can see that each bump right here is the step. The overall activation energy that governs the reaction is the tallest activation energy hill. So that would be this one right here, because it's a lot taller than this one. So this would give you the overall speed of the reaction, not this one, because this is the biggest one. All right, here's a second example of a multi-step mechanism. You can see this one here, and then we've got this activated complex forming an intermediate right here, and then it splits right down here and forms the product right here. And you can see that this is just a little bit exothermic because it starts here and ends down here. All right, we're going to finish with this one, and I'll flip in and out of this, and then I have some answers to write down for it. But this is an old question from an AP exam, and it asks you to do a bunch of different things with activation energy diagrams. So we're going to start actually with letter C right here, and then we'll work backwards and kind of skip around. First of all, it says calculate the activation energy for each forward reaction, show your work. So forward reaction means going from the y-axis where it starts right here and then all the way until it gets to the end. And the activation energy then would be from here to the top of the hill. And so we can see for A, it goes from 30 to 55, and so that would be 25 kilojoules of energy for the activation energy for letter A. And then for letter B, we'd go from 40 up to 80, so that would be 40. And then for letter C, we go from 65 all the way up to 100 right here. And so 65 to 100 is 35. And so just skipping out of here really quickly, you can see that I have A being 25, B being 40, and C being 35. All right, let's jump back to that, and let's ask the second question right here. So in the second one, we've got, I'm going to actually jump to letter A now. Rank the rates from slowest to fastest. So remember, the thing that determines how fast the reaction is how tall the activation energy is. And so if we're going to rank them, the one that would be the slowest would be the one with the biggest or largest activation energy. And we said B was 40 to 80, so that would have the slowest reaction rate because it would have 40 for activation energy. And if you jump back out here, I think we can have this side by side with this. You can see that B would definitely be the slowest, and then 35 would be the middle amount, and then our fastest would be the one with 25, only right here from 30 to 55. All right, jumping back in here, let's look at letter D, I believe we're going to do next. This one says, letter B. Letter B says, calculate the enthalpy of the reaction for each forward reaction, show all work, and indicate if the reaction is endo or exothermic. And so we'll do that by starting here and then ending right down here. And to find the enthalpy, we'll always do final minus initial. And so our final right here is 10 minus 30. So 10 minus 30 gives us negative 20. And that can tell us right away that it is exothermic because it's got a negative value. So that would be negative 20 kilojoules. For this one, we go from 40 to 10. So 10 minus 40 is 30. So it'd be negative 30 kilojoules for that one. And then this one is going to be endothermic, right? Because it goes from 65 up to 85. So we go 85 minus 65, we'd have a positive 20 for that one. So just looking at my results right here, you can see negative 20 for A, negative 30 kilojoules for B, and positive 20 for C. So watch out for those and make sure that you're going from final minus initial to find those. All right, then the last one is kind of a strange question. It says calculate delta H for the reverse of the reaction. Oh, so that means you have to start here and you have to go backwards up to here. So now we would actually call this the end and this the start. So now we'd do 30 minus 10, so it would just be the opposite. It would be 20 kilojoules and it would be a positive value because it would be endothermic in this direction. Here we'd start at 10, go to 40, so this would be positive 30. And then here it would turn into a exothermic reaction. We'd start at 85 and go to 65, so it would be negative 20 for that one. So you can see mine for D right here, they're just the opposite of each one. And of course kilojoules would go on there for each one of the labels for each amount of energy. And you can see the backwards is the opposite of the forward direction. All right, there's a little bit on reaction coordinate diagrams or energy profile diagrams.